Hello, my name is Kip Nieman, and I'm here to present our work on accounting for stress and economic model predictive control for the 2020 AICHE virtual meeting. Today's industries rely extensively on control to automatically maintain process conditions or states such as temperature and pressure at desired levels. The equipment in the process is directly affected by changes in the process variables, therefore process control can impact process equipment. Controllers may not operate at fixed conditions. This could occur in systems under an advanced controller called Economic Model Predictive Control, or EMPC, which can allow for time vary operation, or unintentionally in the case when a cyber attack occurs in the system. In these cases, equipment materials could encounter destructive mechanisms such as fatigue, creep, or corrosion, which depend on the operating conditions. Therefore, simulation of the impacts of control on equipment can provide insights for control design. The traditional approach to process control involves a hierarchical approach with two layers. The upper layer determines system-wide economic optimization in real time, and the lower layer, where control occurs, focuses on maintaining process states at some desired steady state. The lower layer uses feedback control to force the state to remain at some steady state that was determined to be economically optimal by the upper layer. Such lower layer controls can include model predictive control, or MPC, which determines optimal control actions using a model and a quadratic stage cost while accounting for input and state constraints to maintain a desired steady state. The increased needs for integration and real-time optimization in next-generation, smart, and market-driven manufacturing motivates modifications to the traditional MPC formulation. A method of integrating the optimization and MPC aspects involved in process control is through what is called economic model predictive control, which implements an economics-based stage cost. This modification allows economic optimizations to occur within the control algorithm, leading to a controller that can drive systems in a dynamic and time-varying way. First, I want to give some background on economic model predictive control. Here we use a state space description of the process, where the derivative in x, the process state, with respect to time equals a function of x, u, which is the manipulated input of the system, and d, which is the disturbances. We assume the disturbances are bounded, and we assume the function f is a locally Lipschitz vector function. We also use deviation variables to ensure the origin is a steady state. We show the stability of the system by assuming that there exists a stabilizing controller for h of x that renders the origin asymptotically stable, and that a Lyapunov function v exists which satisfies the given equation. Omega rho is a level set of v that represents the stability region. There are many kinds of economic model predictive controllers. Here we apply an algorithm known as Lyapunov-based economic model predictive control. Similar to EMPC, the LEMPC formulation contains an economic cost function, uses a dynamic state space model, implements state feedback measurements, and is able to consider input and state constraints. These are the equations in black. Additional equations are involved with LEMPC, which correspond to two modes. The first mode, shown in red, allows for varying operation while maintaining the state trajectory within the region defined by rho E. If the state leaves this region, the second mode, which is shown in blue, is enforced, which drives the state towards a neighborhood of the steady state. Previous research that applied LEMPC involved a continuous stirred tank reactor, or CSTR, followed by piping, and focused on the mechanical integrity of the pipe. The pipe is thermally insulated, and it is fixed at one end and has a bellows joint at the other end. The fluid temperature at the pipe entrance is equal to the temperature at the CSTR outlet, and the pipe is 2.54 meters long and about 6 millimeters thick. The mechanical properties are also listed here. The reaction of A to B occurring in the CSTR is second order, exothermic, irreversible, and the process is modeled using equations with the concentration of A and the temperature as the states. The economic stage cost applies the reaction rate law and is maximized. The inputs are constrained to represent the limitations of actuators, and we define the decision variables in deviation form. The process states are the concentration of A and the temperature in the pipe, and the manipulated inputs are the concentration of A entering the pipe, which is the same as the concentration leaving the reactor, as well as the heat added or removed from the pipe. The process model is in the input affine form, and the goal is to maintain closed-loop stability via Lyapunov constraints. An h of x controller is applied to each input to ensure that the origin is asymptotically stable. The applied Lyapunov function is quadratic and is of the form x transpose times p times x, where x is a vector of the states and p is a matrix of constant values. In addition, the applied LEMPC parameters and integration step size are shown here. To determine the stress in the pipe, an equation that relates one-dimensional equilibrium stress omega, strain epsilon, and temperature using material properties is applied. The second equation specifically relates stress to temperature in a pipe with a bellows joint. A zero stress temperature of 293.15 Kelvin is assumed. The design stress of the pipe is 10 to the 8th pascals, which is less than the yield stress due to the application of a safety factor. A primary goal in controlling the process is to prevent the pipe stress from exceeding the design stress. Here we compare the results for the process piping of operation at a baseline steady state versus operation under an EMPC designed around that steady state. We assume that at steady state there may be temperature fluctuations due to disturbances that bring the temperature of the fluid leaving the CSTR slightly above the steady state temperature. However, the EMPC ends up increasing the temperature more significantly. This comparison is not fully fair given that the EMPC drives a closed loop state to an alternate higher temperature steady state with greater profits, which implies that it may have been desirable to select that particular steady state instead for the baseline steady state case. We will see that even with this comparison, we are able to describe relationships between control and equipment design. The results of this study demonstrate that the spring constant plays a role in determining whether the piping will be sufficient under a control law. With a very stiff spring constant for the bellows joint, the compressive stress in the piping at the baseline steady state operation condition is not above the yield strength, whereas for the EMPC it would be due to the higher temperature steady state selected by the EMPC. However, with a more typical and lower spring constant, the piping does not reach the yield stress for either control law. This illustrates the concept that if an advanced controller was to operate a process in a new way, the mechanical design and constraints in the controller must ensure that new operating conditions are not outside a range which would allow for equipment integrity to be maintained. To demonstrate how control actions can affect process equipment, a cyber attack that targets the sensor measurement is implemented. On this slide, a typical control loop is shown, with the sensor measurement being compared to the set point to determine the error that is fed to the controller. A cyber attack on a sensor where false state measurements are supplied breaks a traditional control loop. Instead of comparing the sensor measurements to the set point to determine the error, false measurements are compared instead. The cyber attack was simulated with the process under MPC control. Here, a quadratic objective function is minimized subject to the process model and constraints on the inputs. The attack consists of supplying false sensor measurements to the states of the controller. The concentration of A and the temperature were set to 0.05 kmol per meter cube and 440 Kelvin respectively, which are supplied to the controller at each sampling time. The research found that the value of the spring constant Ks impacts the maximum temperature that the pipe can withstand. Lower spring constant allow for a wider operating range due to the decreased force applied on the end of the pipe. This indicates that equipment design can be used as a means for protecting a process from cyber attacks. The prior study provides insight but is limited because of the simplifications applied. These simplifications include the neglecting of transient effects, as the equations for stress only apply to steady state temperatures, and the reduction of the dimensions of the problem to 1. Stress can be more rigorously accounted for through the use of coupled computational fluid dynamics, or CFD, and finite element analysis, or FEA simulations. These simulations are capable of representing the stresses that occur in multiple directions, which form the stress tensor. This tensor contains both normal and shear stress components. We applied the coupled simulation of a steam methane reforming reactor, which is designed to produce hydrogen through the gaseous reaction of mainly water and methane. A steam methane reforming, or SMR reactor, consists of a series of long thin tubes enclosed in a combustion chamber, which supplies heat to the endothermic reaction. The tubes are packed with catalysts to facilitate this reaction. We used ANSYS Fluent to replicate a simulation from WOW and others of the transient fluid flow through a single tube. Custom user-defined functions, or UDFs, were created to add custom functionality to the simulation. This includes the heat applied to the outer tube wall, which is a function of the length Z. Tmax wall represents the maximum temperature achieved through the control action of the burners. Another UDF applies proportional or P control with a gain of 1,856.3. A third UDF supplied the reactions shown and the rate laws to the simulation, which come from a zoo and ferment paper published in the AICHE journal. Additionally, the K epsilon wall model with enhanced wall treatment was applied to represent fluid flow near the tube walls, and a porous zone formulation was used to represent flow through the packed bed. We extended this fluent simulation by coupling it to a solid mechanics simulation using ANSYS Mechanical. For material properties, the tube was assumed to be made of HP grade stainless steel, which has been used in SMR reactions previously. The simulation exports a temperature and pressure profiles from fluent to act as loads in the mechanical simulation in a one-way coupling setup. The tube was assumed to have a fixed displacement boundary condition at the inlet, atmospheric pressure on the outer wall of the tube, and gravity. The temperature results are shown here for the case of a cyber attack. The figure on the left shows the temperature profile near the inlet end of the tube at the start of the simulation, where the process is operating at steady state. At 0.1 seconds, a cyber attack that targets the sensor is activated. The sensor reading is detected to be a low value, which causes the controller to increase the temperature to the maximum bound in response. The consequences of this attack can be seen in the figure on the right. It can be seen that the solid temperature, which is represented at the top and bottom of the figures, increases significantly while the fluid temperature is relatively unaffected. Such simulations could be used to predict the impact on process equipment of various cyber attacks on a system, acting as a test bed. These figures demonstrate expected axial normal stress trends at two different points in the tube wall over time due to this cyber attack. The rapid temperature change leads to a spike in the stress, which directly indicates the attack on the equipment. Overall, this work reviewed efforts to rigorously account for control impacts on process equipment materials. Prior work utilizing only a steady-state thermal stress analysis in one dimension is insufficient to model most equipment conditions, including with economic model predictive control or under cyber attack scenarios. The coupled CFD and FEA simulations in ANSYS enable process simulation results to be coupled with analysis of stress and strain in process equipment, which allows us to investigate how a sensor measurement cyber attack can affect the steam methane reformer. Finally, we gratefully acknowledge our funding sources, which include the Air Force, the National Science Foundation, and Wayne State University. Thank you very much for taking the time to view my presentation.